Now, let's move to a new idea, infinite limits. Sometimes a function grows without bound as x approaches a certain number. This means the function keeps increasing or decreasing and does not settle at a fixed value. If f of x increases without bound as x approaches a, then we write the limit of f of x as x approaches a equals infinity. This does not mean the limit is a real number. This means the function is growing larger and larger without stopping. If f of x decreases without bound, we write limit of f of x as x approaches a equals negative infinity. This means the function is going down without bound. Infinity and negative infinity are not fixed numbers. So when we write limit equals infinity or negative infinity, that means the limit does not exist. We are using infinity and negative infinity to describe the behavior. It just tells us the function keeps increasing or decreasing. Now, let's evaluate this example. Limit of the function 1 over x squared as x approaches 0. As x gets closer to 0, x squared gets very small. And 1 divided by a very small number is going to be a large number. So let's use an example. Say if I let x be 0.01, and 1 divided by 0.01 squared is 10,000. Imagine if I choose a number that is even closer to 0 than 0.01, then this number even gets larger. Now, let's choose a number on the left of 0, say negative 0.01. 1 divided by negative 0.01 squared is also 10,000. And imagine if I chose a number that even closer to 0 than negative 0.01, then this number even gets larger. So the limit of 1 over x squared as x approaches 0 is infinity. When a limit equals infinity, that means the limit does not exist. Infinity just tells us that this function is increasing without bound. So today, we learned two important ideas. First, two-sided limit exists only if the left-hand limit equals the right-hand limit. Second, if the function grows without bound, we describe it using infinite limits. And remember, infinity and negative infinity describe the behavior. They are not a real number. Now, let's move to our new topic, vertical asymptotes. A vertical asymptote occurs when a function has an infinite limit at a given x value. In other words, as x approaches some number a, the function decreases or increases without bound. When that happens, we say the line x equals a is the vertical asymptote. The line x equals a is a vertical asymptote of the function f of x if the limit when x approaches a from the left of the function f is either infinity or negative infinity, or the limit when x approaches a from the right of the function f of x is either infinity or negative infinity. Notice something important? We only need one side to go to infinity for there to be a vertical asymptote. It doesn't matter if both sides go to positive infinity or both go to negative infinity or one goes to positive infinity and the other to negative infinity, as long as the function grows without bound near that x value, there is a vertical asymptote there. If you look at these graphs, you see the vertical dashed line at x equals a. As the curve approaches that line, the function either shoots up or down. It does not cross the line. It just keeps increasing or decreasing. The dashed line represents the vertical asymptote. Now, let's identify the vertical asymptote for this function, f of x equals 1 over x minus 3. We are going to do this in 2 steps. First, we'll find the vertical asymptote algebraically without looking at the graph. Then, we'll use the graph to confirm our answer. To find the vertical asymptote, we ask one key question. When is the function undefined? Since this is a rational function, it is undefined when the denominator equals 0. So we set the denominator equal to 0. And we are going to solve for x. So we're going to add 3 to both sides. The function f of x is undefined when x equals 3. Now, we check what happens near x equals 3. If x gets close to 3 from the left side, the function goes to negative infinity. And if x gets closer to 3 from the right side, the function goes to positive infinity. So, the line x equals 3 is my vertical asymptote. Please note, a vertical asymptote is the equation of the line. It's not just a number. When we say the vertical asymptote is x equals 3, we're not saying 3 is the asymptote. We're saying the vertical line with the equation x equals 3 is the asymptote. So, x equals 3 is the equation of this vertical line at x equals 3. It's not just a value of the function. It's the equation of the line on the graph. Now, we're going to use the graph to determine several values. We are given the graph of function f of x, and we will carefully read information from it. Remember, open circles show where the function is not defined. Closed dot shows the actual function value. For limits, we look at what the graph is approaching to. For function value, we look at the closed dot. For question A, as x approaches negative 4, we look at the left-hand limit, right-hand limit, two-sided limit, and the function value at x equals negative 4. For the left-hand limit, we look at what the function is approaching to when x is approaching negative 4 from the left. Look at the graph. As x approaches negative 4 from the left, the curve is rising toward x-axis. It appears to approach 0. So the left side limit of f of x as x approaches negative 4 is 0. Now, when x approaches negative 4 from the right, the graph is also approaching 0. So the right side limit is also 0. Since the left-hand limit is 0, the right-hand limit is 0, so the two-sided limit is also 0. For the function value at x equals -4, there's no open circle or closed dot shown at that point. The graph appears to pass through it, so f of -4 is also 0. For question B, I want the left side limit of the function f of x as x approaches -2. As x approaches -2 from the left, the graph approaches the open circle at y equals 3. So the left side limit is 3. For the right-hand limit, as x approaches 2 from the right, the graph also approaches that same open circle at y equals 3. So the right-hand limit is also 3. To find the limit of f of x when x approaches -2, we look at the left-hand limit and the right-hand limit. They both equal 3. So the limit of f of x when x approaches -2 is 3. For the function value at x equals -2, we look at the graph. There is an open circle on the curve at x equals -2. That means the function is not defined here. Now check to see if there's any closed dot at x equals -2. No. That means the function is not defined at x equals -2. Question C, we're going to find the limit of function f of x when x approaches 1 from the left side. As x approaches 1 from the left, the graph approaches the dot at y equals 6. Now, for the limit of f of x when x approaches 1 from the right, as x approaches 1 from the right, the graph approaches the open circle at y equals 3. To find the limit of f of x when x approaches 1, we check the left-hand limit and the right-hand limit. Are they equal? No. Since 6 does not equal 3, the two-sided limit does not exist. To find the function value at x equals 1, we look at the closed dot at x equals 1. It is at y equals 6. So f of 1 equals 6. Question D. Find the limit of f of x as x approaches 3 from the left. As x approaches 3 from the left, the graph drops down toward -infinity. Limit of f of x as x approaches 3 from the right. As x approaches 3 from the right, the graph also drops down toward -infinity. For the limit of f of x as x approaches 3, since the left-hand limit is -infinity and the right-hand limit is also -infinity, so the limit of f of x as x approaches 3 is -infinity. Remember, -infinity means the function decreases without bound. It also means that the limit does not exist here. To find the function value at x equals 3, we look at the graph. There's no closed dot at x equals 3. And the function decreasing without bound at x equals 3. That means we have a vertical asymptote at x equals 3. So the function is not defined at x equals 3.